Welcome back to school. This is so weird. Um, I don't know. I hope you guys are enjoying your isolation in some kind of weird sense. Not that there's anything really good about this whole situation. Um, it feels like it's been forever since we were all in school. Um, I don't know. I'm not really a big fan of this whole thing. I think I'm ready for the coronavirus to go away and for things to go back to normal. A week, I don't know, a week and a half is long enough. Um, but unfortunately, the universe doesn't usually listen to me when it comes to these things. So, anyways, you can say hi to Pablo. Hi, Pablo. Um, so I hate recording myself, so I'm gonna try to make this short. Well, to be fair, I've already recorded things for one of my other classes, and I was not successful at making it short. So this probably won't be either. But let's get down to it. So um, we finished off the last time I saw you about 3 years ago, when slightly before the world was ended. Um, we were talking about electric charge, different ways of charging things up using the Triboelectric Effect, which relies on friction to move charges from one surface to another. Um, we did some experiments. You guys did a lab where you investigated the different ways of doing this. What we're going to talk about now are some of the effects of charges in a more quantitative way. So we know that charges repel and attract each other. Um, what we're going to talk about now is how do they do that? What is the mechanism that they use to do that? So let's get started. So, what did we just see? Well, all the little pieces of styrofoam were in the little container, and then they flew off and hit the ground. So first, this thing over here um, is called a Van de Graaff generator. Um, and what it is there's this metal sort of sphere-shaped thing at the very top. Um, and if you look closely inside this plastic tube, you can see that there are these like vertical stripes. What this is a belt, and it runs up and down. And at the bottom, this belt is in contact with a material. And at the top, this belt is in contact with a different material. And there's a motor in here that causes the belt to run, actually pretty fast. And what happens is, because the material at the bottom is different from the material at the top, the triboelectric effect results in a transfer of charge from one end to the other. A typical Van de Graaff generator actually results in an excess of positive charges up here, which means that the belt actually removes electrons from the top, brings them down to the bottom, where it deposits those electrons onto a material in the bottom, and those are actually then whisked away through this wire, through grounding, so that we end up with a positively charged metal sphere at the top. And so, based off of what we've learned about different methods of charging, we can guess what's going on over here. So, this tin plate, or technically aluminum foil plate, is really here just to provide a container to put the styrofoam things in. And aluminum is conducting, which means charges can easily move from this shell onto this plate. And these little pieces of styrofoam were sitting inside of here. And so everything was in contact. And so as this dome becomes positively charged, it starts to steal electrons from the aluminum tin, the aluminum bowl, plate, I forget the name, container, there we go. And then the aluminum container starts to siphon electrons from the styrofoam that's sitting inside. And so everything up top becomes positively charged. And styrofoam is really light. So when you have a really light object starting to become positively charged, sitting on top of a very strongly positively charged object, it tends to result in everything flying apart. And so let's go back and let's play it again, and we'll see, well, just for fun. We know why this happens. We know that we know from what you learned in chemistry and from what we've done with our classroom demonstrations and the lab that you did. We know that when you have two like charges, they push each other away, right? They repel. Now, on the other hand, if we have two opposite charges, they tend to pull each other together. But what is it that causes this attraction and this repulsion, right? So there's obviously a force, right? We call that the electric force. The force between charged particles that causes them to push and pull on each other. But these charges are not touching each other. It's not like a normal force that we've described. It's not like a tension force, right? These forces are happening between particles that are far away from each other. They are not, reaching out and touching each other. There's no string between them. So we have to figure out what it is that's actually doing this. Now, we've seen an example like this before. You might be able to think of a very similar example. It's a force that we feel all the time, and it's gravity, right? So even if you're falling through the air, you still feel the force of Earth's gravity pulling down on you. Earth is not touching you, but somehow it's affecting you even though it's far away from you. And the mechanism that we describe this kind of interaction through is a field. So with gravity, we would call it the gravitational field. With charges, we call it the electric field. So just like if you were on Earth, or not on Earth, but if you were, floating somewhere above Earth, you would still feel a force pulling you down towards the Earth. We would call that the force of gravity. That force is caused indirectly by the mass of the planet below you, but it's caused directly by the gravitational field at your position. Earth creates a gravitational field. It creates a gravitational field everywhere in space. And it always pulls inwards, right? The gravitational field always attracts things to the Earth. Earth's gravitational field always attracts things to the Earth. The sun's gravitational field attracts things to it. Gravitational fields are always attractive, so this is a little bit different because with electric fields and forces, we can get both repulsions as well as attractions. So what I've drawn here is an example of something that we call a field line diagram. I've drawn a bunch of field lines. The lines are continuous and they have a direction, which is what these arrows represent. And in reality, it's more of an analogy or a metaphor for what the field is, because the field, it's not like it exists here and not in between, right? The field is everywhere. The difference is I can't actually draw an infinite number of lines, or if I did, it would just fill the entire page with green. So we draw these field lines to be representative of electric fields. Now, there are a couple things that we can actually learn from a simple diagram like this. One is, you'll notice, if you think about it, or when, oh my God, I was about to ask a question, like expecting an answer. Anyways, so Earth's gravitational force on you is greatest when you're near the Earth. If you're far away from the Earth, then Earth's going to have a relatively small effect on you. And so somehow that should be reflected in the field. The field should be stronger when you're closer than when you're farther away. And you'll notice there is a feature of this diagram that is representative of that. I've drawn a certain number of field lines. The number of lines that I've drawn is kind of arbitrary. However, this feature that they are closer together near the Earth than far away from the Earth is important. And it actually gets us to one of the rules about how to interpret field line diagrams, which is that denser regions, so regions, let me phrase it differently. Denser field lines imply a stronger field. So if I draw a field, or field lines, then wherever the lines are closest together, the field is strongest. And whenever the fields are far apart, the field is weakest. So this is a nice little heuristic to allow us to look at a simple picture and actually see a fairly large amount of information about the nature of the field created. In the case of the Earth, we see that a field always points towards the Earth, and we see that it is stronger closer to the Earth and weaker farther away. Now, this diagram is not perfect, and we actually often represent things a little bit differently. So let's look at how else we might represent an electric or a field in general. So let's stick with gravity, and let's talk about the Earth again. We know that the field is strongest near the Earth, and it's weakest farther away. And it has a direction, right? It points towards. So we've talked about things that have directions as well as magnitudes. We call those vectors. So we can represent the field with vectors. Now the field is a different vector everywhere. Near the surface of the Earth, it points inwards, or rather it always points inwards. Let me actually draw this a little bit differently. Near the surface of the Earth, I'm drawing it as pretty large vectors representing the strength. So as you get farther and farther away from the Earth, you would expect that the field would get weaker. And so let's draw that. I want to draw the field maybe over here. The field is going to be weaker over here than it was in the middle, so the lines should be shorter. But I want to make sure that I'm drawing all these new ones at the same distance. And I can draw more field lines from even farther away, and again, those should be even weaker. Something like this. Now, this is, a very rough sketch on my part, but this kind of diagram is called a vector field diagram, because now we're representing this field as a bunch of little vectors instead of a bunch of lines. So our previous example looked something like this, where we have lines. We have to infer the strength of the field by how far apart the lines are in different places. But a vector field diagram makes the strength explicit. If I drew this diagram to scale, I could literally measure what is the length of this vector and what is the length of this vector, and I could easily calculate or determine the relative strengths of the different places. So a vector diagram is typically considered a superior diagram. It gives more information. However, vector field diagrams are a pain in the butt to draw. As you may have noticed, I I paused the recording and I finished the diagram so you wouldn't have to sit and wait through me drawing the whole thing. So these are two different ways that we can represent a field. And again, there are two ways of representing the magnitude and the direction of the field. But what does the electric field of a charged particle look like? Does it look like a gravitational field from a planet, or does it look different? So let's look at another demonstration and try to figure that out. The previous demonstration that I showed you wasn't ideal because it only showed the positively charged styrofoam pieces being pushed away by this dome for a short period of time, right? They were on top, they got knocked off, and that was it. So we didn't really get a good picture of things. So what he's done here is he has attached these styrofoam pieces through string to the top of the Van de Graaff generator, to the dome. Now the string, even though it's an insulator, the Van de Graaff generator produces such a large charge that it can actually charge this entire piece, the styrofoam pieces, through the string. It'll actually push enough charge that everything will once again become positively charged. And if we look at how these things behave, we should be able to get a good idea of what the electric field is doing and what the force is being experienced by these styrofoam, what are they called? Styrofoam peanuts? I feel like that's not the right word. I'm going to call them styrofoam peanuts. So let's watch it. So now that the styrofoam things are stuck in place, we see that they just get pushed away, right? The styrofoam pieces are pushed almost directly away from the positively charged dome, even the ones directly on top. So first of all, we've seen an interesting thing. This little dome is strong enough to completely overcome the effects of gravity on this styrofoam peanut. That's definitely not the right word. It just points directly radial away. So this actually does look a lot like our field line diagram that we drew for the Earth, right? For the Earth, we had it like this. We drew our field lines, and they pointed directly towards it. This is a terrible picture, but you get the idea. So we're seeing something similar happening over here. Now, there are some important distinctions. For example, look at the direction that these are experiencing forces, right? The Earth pulls things towards us. These are being pushed away. So maybe instead of looking like this, maybe the electric field made by this Van de Graaff generator looks more like this, with the lines pointing away. But qualitatively still pretty similar. So that's a pretty good indication that we're looking at something similar to the effects of gravity and that we can represent it in a similar way. So we have a roughly spherically shaped charge, and it's repelling other like charges directly away from it. Analogous to how the Earth pulls other masses directly towards it. Here's another variation of the demonstration where we use a piece of string to see the same thing. The string is always pushed away from the metal dome, wherever we hold it. Now we're going to watch another demonstration. This one actually makes use of a straw that's cut in half and pinned to the tip of a meter stick so that it's free to swivel. And so this straw will actually tell us what direction the field is pointing. And so as we move it around the Van de Graaff generator, we see that it swivels so that it always ends up pointing directly away from the Van de Graaff generator. So again, we see lots and lots of evidence that the field has to be radial. It seems to be pointing away from the Van de Graaff generator. And so let's sort of quantify this a little bit. So if I have a positive charge and I take a another positive charge and I place it over here, the big one in the middle is like our Van de Graaff Generator dome, and this one is like the little peanuts suspended somewhere around it. Now, we've established that the little positive charge over here will be pushed in that direction, away. And if I instead put a little positive charge over here, it would be pushed away. Even stronger because it's closer. That might be an exaggeration, but whatever. And I could do the same thing. I could put a little charge over here, maybe even closer. No, I don't want to draw such a big arrow. Maybe somewhere over here. This little charge would be pushed away with a force, maybe somewhere in between, because it's about halfway between. Well, I guess it's closer to that. Actually, no, this is even closer. I drew that terribly. Let's do that again. So if I have my little charge and it's something like here, it's somewhere in the middle between, how far away this one is versus how far away this one is. So the force will be somewhere in between. And once again, it'll be pointing directly away from it. So wherever we place this tiny little positive charge, it's going to experience a force away from it. This is actually a method of measuring a field. And what we call these little positive charges test charges. A test charge is a hypothetical or actual positive charge. And the reason why we bother giving this a name is if I want to know what direction does the field point, what I can do is I can say, well, if I were to place a positive charge right here, what direction would it experience a force? And how big of a force would it experience? And I don't need to actually place the charge there if I know information about the field. But if I don't know information about the field, I can measure the field indirectly by measuring the resulting force on this little test charge. So we can infer something about the field from this force. Now, before we start talking too much about forces, I want to actually focus on the field. So what we're going to do is erase the test charges. Because I don't want to know what is the force on a charge at a certain place. I want to know what is the field at this place, and at this place, and at this place. And just like gravity exists, whether there's something there for gravity to pull on or not, the electric field exists even if there are no charges there to be pulled or pushed on. And so, by convention, so we see that the positive charge pushes away the other positive charges, and by convention, we say that positive charges create electric fields that spread outwards. They spread outwards radially in every direction. And so it'll look like something like this, where we have our field line diagram. I've drawn a field line diagram, not a vector field diagram, because I'm lazy. Now, technically, these field lines should all extend all the way away to infinity. However, drawing lines that long stretches my ability to draw straight lines, so I have cut them off. But in reality, they should keep extending forever. So this is what we would call an electric field line diagram of a positive charge. And we see that it points away from the positive charge. Now, I know that if I did put a little positive charge right here, it would experience a force in that direction. And we can relate these two together by saying that the electric force experienced by this positive charge is equal to its charge times the field. But force is a vector quantity, and fields are also a vector quantity. We established that. And so this is really a vector equation where the force is in the direction of the field. And so if I place a positive test charge, if this test charge is positive, then it will experience a force away. If Q is greater than 0, then F is in the same direction as E. In other words, positive charges are pushed in the direction of the electric field. But if Q is negative, then F is proportional to the negative of the electric field, which means negative charges experience forces in the opposite direction of an electric field. So if I were to take a little negative charge and put it right here, since the field at this location is pointing away, if I draw another line there to represent it, then the force experienced by this negative charge would point inwards in the opposite direction that the field points. So this is a fundamental difference between electric forces and gravitational forces. Everything is pushed in the direction of the gravitational field, everything with mass, right? The gravitational field points inwards towards the planet, and everything falls inward towards the planet under the effects of gravity unless something else is acting on it. Whereas with electric fields, positive charges experience the same thing. They get pushed in the direction of electric fields, whereas negative charges get pushed in the opposite direction. They go backwards. Let's draw something similar, except this time let's draw the effect of, or the field from a negative charge. One way I can do this is I have my negative charge. I can do a little experiment. Because I know how charges behave near each other, if I put a little positive charge right here, I can think, well, what direction will this positive charge be pushed or pulled? It's going to be pushed towards, or pulled towards, the negative charge. Now, we established over here that positive charges experience forces in the same direction as the electric field. And so if the positive charge is pushed this way, inwards, that implies that the field lines of the negative charge need to point inwards. And that's not really a straight line, but whatever. And if I put a positive charge over here, it would also be pushed inwards. And over here would also be pushed inwards. And over here would also be pushed inwards. And same over here. And no matter where I put this thing, it would always experience a force directed towards the negative charge. And so a negative charge creates an electric field that points inwards, that points towards it. So we can come up with some rules of thumb, which are that electric fields that's not how you spell electric fields. Electric fields point towards negative charges and away from positive charges. We also know that positive charges experience forces in the same direction as the electric field they are in, and negative charges experience forces in the opposite direction. Of the field they are in. Now, it's also worth noting that charges only experience the fields of other charges. This is very much like how the Earth doesn't pull itself around by its own gravity. So the sun doesn't pull itself around through its own gravity. The sun attracts the Earth to it. The Earth attracts the sun to it, but they each don't attract themselves to themselves. It's just not how it works. They experience the fields of other things. Earlier, we wrote down the equation that the force experienced by a charge is equal to its own charge times the electric field that it's in. Now, it's really important to note that this Q here is the charge experiencing the force. It is not the charge creating the force. The electric field is created by a separate charge entirely. The external field from a different charge creates a force F on charge lowercase q. This is really similar to the force of gravity, right? The force of gravity is equal to mg, where the force of gravity, F, is created by a gravitational field, G, and the force acts on mass m. And little m is not the force that creates the field. And if you recall, we generalized this using Newton's law of universal gravitation to gm1 m2 over r squared, where we can write little g as capital G times m2 over r squared. And so we see that the gravitational field is created by m2, and it's experienced by m1. m1 experiences the field created by the mass m2. And it also depends on the relative positions of the two objects. There's an analogy between Q and m here. M tells us how big a force of gravity the object will experience due to some external field, and charge does the same thing. It tells us how big will the charge the object experience due to some external electric field. And so we actually often call M1, or M here, the gravitational charge, just like we call this the electric charge, because they each fulfill the same role with their respective forces. You also might not be used to thinking of little g as the gravitational field itself, because we usually think of this as the gravitational acceleration. But it just so turns out that the gravitational field has units of acceleration, and we can interpret it that way. But that raises the question, what are the units of the electric field? Based on what we just said and how we described the electric field, you should be able to actually figure out what these units are. So why don't you pause the video and take a moment to determine the units here. Okay, honestly, that was just an excuse for me to mute my audio so I could sneeze. But since we know that the electric field can be expressed as the force experienced by the charge divided by its charge, well, the units are the units of force divided by the units of charge, which is a Newton per Coulomb. So these are our units of the electric field. Now, these units actually make a lot of sense. So, for example, let's consider we have an electric field equal to 20 newtons per Coulomb in the plus x direction. Let's call that to the right. Well, if I take a positive charge with 2 coulombs of charge, it will experience 20 newtons for every coulomb of charge that it has. And it's positive, so it will experience a force in the same direction as the field. And so it's going to experience a force of 40 newtons to the right. If, on the other hand, I had a negative charge, negative 2 coulombs, well, it still has 2 coulombs of charge, so it's still going to experience 40 newtons, 20 coulombs for every charge. However, because it's negatively charged, it's going to experience a force in the opposite direction, but still of 40 newtons. And so the units here are really descriptive of what's going on. It simply tells us how big of a force an object will experience as a function of how much charge it has in the presence of this particular electric field. Now let's talk about what happens if we have multiple electric fields in the same place. So for example, what if I have a bunch of charges situated all over the place? How are their fields going to interact with each other? Well, it turns out that we describe this using a principle that we call superposition. It seems like a silly word, but it's actually an incredibly or super important concept in physics and math. And really what it tells us is that the combination of 2 or more fields is the vector sum of the fields at every position. So it sounds like it's really just a fancy word for stuff adds, which it basically is. It basically is just telling us that electric fields are nice enough that if I put 2 of them, if I have 2 of them sharing the same space, they just add together. Now they're vectors, which means we have to add them like vectors, but it's still just addition. There are things in the universe that don't behave this way. The strong force, for example, does not exhibit this. It kind of interacts with itself. We call it nonlinear, so it does not exhibit superposition. But electric fields are well enough behaved that we can simply add them together. So one of the reasons why we call it superposition is because if I have one electric field at a certain place that's represented by a vector like this, let's call it E1. Again, this is just at one particular place. And at the same place, a vector E2 has a field that does something like this. Well, I literally just superimpose them. I add the 2 vectors together, and so I can add E2 over here, or I could add E1 to the end of E2, and the result, this green vector here, is the total field created by E1 plus E2. So I'm literally just adding vectors together. Now, the rub is that I have to do this everywhere, right? Because there is also a value of the electric field of E1 and E2 over here. So I have to add 2 vectors here and 2 vectors here and everywhere you can think of. And the vectors might change from place to place, and they might change in different ways. So the result can give very complex patterns, but the process of finding those patterns is pretty straightforward. A really common example of this is called a dipole field. The field created by 2 nearby positive and negative charges of equal magnitudes. Consider these 2 charges, a positive charge over here, a negative charge over here, each with their own vector field diagram. So the little vectors here represent the magnitude and direction of the fields that each of these charges create. The negative sign is missing here, I don't know why, but this green one is negative. And what I'm going to do is I'm going to bring them closer together so we can see what happens. We can see what happens when I take these 2 charges and I start to bring them closer together until their field diagrams start to overlap with each other. And it's not perfect because the lines don't perfectly line up with each other. But we can start to get a feel for what this is going to actually look like, this resulting dipole. So let's start to draw some things. So first of all, we note that in the middle, the fields from both charges point in the same direction. So there's going to be a strong electric field. I'm going to draw this in blue so maybe it's more visible. There's going to be a strong electric field pointing this direction because they're going to add together. But on the other hand, over here, the positive charge creates a field to the right, but the negative charge on the right-hand side creates a field to the left. So over here, they're actually going to cancel each other out a little bit. Over here, and then the same thing is going to happen over here. Now, just like with gravity, we see, and we're going to talk about this more in a bit, that the farther away we get from this charge, the weaker the field gets, and that makes sense. I think that's to be expected. Again, we'll talk more about it in a bit. But there are a couple other interesting things. You'll note, for example, down here in the middle, the electric field from the positive charge points up and to the left. The electric field from the negative charge points down and to the left. Well, the up and the down are about evenly matched. So those are going to cancel out, leaving only a field pointing to the left. So if I want to, that means right over here, I expect the field to be pointing to the left. And I can do the same thing over here. The up and the down components of our, I'm going to make this a little bit fatter, of our field cancel out, leaving only the sideways or horizontal bits of our field remaining. Now, it's a little bit harder to do. There are not enough vectors to show it entirely, but what this is going to end up looking like is when you're very near the positive charge, it's going to win because you're very close to it, so it's going to be the strongest. So it's going to be more or less pointing up. This is going to be more or less pointing this way. This is going to be more or less pointing outwards, and so on. All of these are going to basically just do what we would expect a positive charge to do, and the same thing will be true of our negative charge. When we're very close to it, we expect the field to point towards it. But we see that over here, right, it points to the left. And what happens is when we get farther and farther away from the charge, the effects start to balance out between the two. Then as we get closer and closer to the positive charge starts to overcome the negative one. And we can do the same thing on this side. So it's going to look something like this. And let me erase this part over here so it's just a little bit less messy. And our field starts to look something like this. It bends from one charge to the other. And the same thing will actually be true over here. It's going to look something like that. And in fact, these ones, this line over here, as it gets farther and farther away, so the positive charge is creating a field pointing just straight up and to the right. But if I'm over here, the negative charge is going to exert a field pointing a little bit that way. And the effect is that it causes the line to sort of bend ever so slightly. And so the field line is going to do something like that. And same with this one over here, and same with this one over here, and same with this one over here, and so on. And so this is what our diagram looks like. Now, this is a big, awful mess. So what I'm going to do is I'm going to show you a much nicer picture that shows what the ultimate effect of this is. It looks a bit like this. So this actually looks like some kind of like, I don't know, frog face or something. But this is what a dipole field looks like. The field starts from the positive charge because fields point away from positive charges, and it gets pulled or bent inwards towards the negative charge. I shouldn't say pulled because there's no force over here, right? These represents fields, not forces. So the field lines are bent inwards. They're curved because what we're doing is we're simply adding at each point a sum of two vectors. So for example, right here, there is a force pointing towards the negative charge like this and pointing away from the positive charge like that. That's a bad diagram. So if I extend this like this, it points towards that. And if I extend this like this, it points towards that. And so the field from here points something like this. And because they're equally far away from each other along this vertical middle line, the magnitudes are going to be the same. It's only their directions that are different. And so when you add the effects of these two fields, the vertical components cancel out and you're left with just the horizontal bits. And that's why the field points horizontally right down the middle. So this is a graphic that shows different fields of different configurations of two charges. So on the top left, we have the fields of a positive charge. Top right, we have a negative charge. On the left, we have a dipole field, just like we just showed. And then these two are what it looks like if you have two charges that are like each other. In the end, so if they're two negative charges, the fields point inwards towards the negative charges. But in the middle, they cancel out because right here in the middle, if we think about this, the field from the charge on the left points towards it like that, and the field from the charge on the right points towards it like that. And so they cancel out. They produce no net field at all right in the middle. And if I think about what's going on right over here, the one on the left is pointing like that, and the one on the right is pointing like that. And so, like in the dipole, the result was that the field was horizontal there, but with like charges, the field actually ends up pointing vertical. And so we get a field pattern that instead looks a little bit like this. There's not really a name for this particular kind of field, but it's what the electric field looks like due to two like charges. The only difference over here for the positive charges is that the direction of the field lines are the opposite direction. Next, let's investigate the creation of the field, right? So let's go back and let's talk about the charge that creates the field, and we want to be able to figure out how can we determine the electric field caused by a particular charge. So here's the thing. We know that if I have a charge here, let's call it positive. If I imagine a little test charge over here, I'm going to make it positive, but it could be negative. We know that the electric force over here, it'll be pointing away, but forget the direction for now. I just care about the magnitude. So if I have these two charges, let's call this one capital Q, and let's call this one lowercase q. And in fact, let's leave out the sign of this test charge over here. Lowercase q is ambiguous. We don't know whether it's positive or negative. Well, we know that the force is probably going to depend on these two charges. And if this charge is really big, we would probably expect a really big field, right? If the charge is 0, we would expect no field. So if the charge is big, we'd expect a strong field. Likewise, if charge is what determines the strength of the force acting on an object created by a field, then it should also affect how big the force is. And so we would expect that the magnitude of the force would depend on the magnitude of the sums of the two charges. So I think that's reasonable. It satisfies our qualitative observations and it satisfies our intuition, and we're going to go with it. And it turns out to be right. Now the next step is, how does the distance between these two charges matter? So let's call this distance r. This is a little bit trickier because there are a lot of options, right? As you get farther away, we expect the field to go down. So we expect it to maybe have an r in the denominator. But maybe it's not r, maybe it's r cubed in the denominator, or maybe it's something else. It turns out that it's not just anything else, but in fact, it turns out to be 4 pi r squared. And you might think, why 4 pi? Where did that come from? R squared, maybe, okay, sure. But why 4 pi? What is even the point of that? And this comes from the same place that it does with gravitation, although we didn't really see the 4 pi with gravitation. And where it comes from is this. If I have a charge right here, or not even a charge, if I look right here, this negative charge in the center is creating the electric field that we're worrying about. Well, as I get farther from it, that field is spreading out over a greater region. And when I'm really close, the field is spread out, stretched out over the surface area of this sphere, of the shape of the charge. But as I get farther and farther away from it, the field is spread out over an increasingly large sphere. And if I go even farther away, the field is spread out over an even bigger sphere. These look like circles, but imagine it three-dimensional. And as we get farther and farther away from the central charge creating the field, again, it's spreading out over this entire surface of this expanding sphere. And the surface area of a sphere is 4 pi r squared. And that is exactly where this factor of 4 pi r squared comes from. This is called an inverse square law. And it happens almost any time you have a central object or source of a field or other phenomenon that then spreads out over a three-dimensional sphere. So for example, if I have a light bulb and I stand, and it's right here in the middle, and I stand this far away, I will only experience the portion of the light that actually hits my eye. If I stand this far away, my eye will actually capture less of the light. So for example, let's say this is the light bulb. If I stand really close, this is my eyeball, then the light from the light bulb, all of this light will hit my eye. But if I draw my same eyeball farther away, it looks a little bit bigger, but imagine it's the same size. If I extend the rays of light, you'll see that now a lot of the light that used to hit my eye now goes right past it. Only this much of the light hits my eye. And the surface area that the light has to spread out over is exactly 4 pi r squared. So this is another example of an inverse square law. This is why if you stick your face right up to a flashlight when you turn it on, it's blinding and it hurts, and I do it all the time. I can't help but do it whenever I turn on a flashlight. It's like a compulsion. Not intentionally, it's just like, I think my brain just thinks, oh, well, how will I know if it turned on if I'm not looking at it? Anyways. But if you're standing far away from someone and they turn on a flashlight pointed at you, it's probably not a big deal. That's because you're farther away, and so much less of the light actually reaches you. And again, it is this factor of 4 pi r squared. So this is our equation for the force that we expect two charges to experience. It's a little bit problematic because the units don't quite work. But before we even worry about the force, let's go back because we established that the force experienced by charge Q is equal to its charge times the electric field. And let's just talk about magnitudes for now. Forget directions. That implies that we can rewrite the field as force over the charge experiencing the force. And based off of what we wrote above, we can write this as the central charge that created the field divided by 4 pi r squared. Now it turns out that there is actually a missing constant here. There's actually an epsilon naught in there. This epsilon naught is called the permittivity constant. I forget its value. You can look it up. It might even be on the reference table. But this, in particular, this is the electric field created by a point charge, capital Q. So if I have a charge, capital Q, here in the middle, if I want to know what is the value of the electric field at this position, the electric field here is simply equal to Q over 4 pi epsilon naught r squared, where r is the distance from the center of the charge that created the field to the position of where I'm looking at the field. We put in the directionality by hand. I know that the field points away from a positive charge towards a negative charge, so we are going to make this an absolute value. Now, 4 pi epsilon naught is often rewritten. We often rewrite this as simply k times q over r squared, where k is called Coulomb's constant. And I just realized, it's simply equal to 1 over 4 pi epsilon naught. And it just simplifies the equation. There's less to deal with. Now, the way of expressing it over here is really the more fundamental way. The 4 pi is intrinsically related to how the field is spreading out, and epsilon naught is a very important constant in physics. It's related to the strength of electric fields. It's related to the speed of light. Whereas k, Coulomb's constant, doesn't really have any particular meaning on its own. It is worth noting that this is the original way that we wrote this equation. K was measured by a guy named Coulomb, hence Coulomb's constant, and he didn't really understand or know why the force between charges was this, but he measured that it depended on their charges and that it depended, or fields created by a charge was this, but he measured that it depended on the charge creating it. He knew it depended on how far away you were. He could measure that. And there was just this constant, and he experimented to find what the value of this constant was, and it was something like 9 times 10 to the 9 of whatever units it needs to have. And I'm going to leave it as an exercise for you, and you should do this. What are the units of Coulomb's constant? So we're going to leave that here. We've done a whole lot. So you have a homework assignment on the Google Classroom. It hopefully shouldn't be too hard, although I've never taught this remotely before, so maybe you're all super confused right now, and we'll deal with that if that's the case. Either way, if you are confused or stuck or have any other concerns, please reach out to me. You can reach out to me by email, from the Discord server, you can talk to me during the office hours on Zoom. You'll be getting an announcement about that on Google Classroom. Actually, you should already see it because I scheduled them to all happen at the same time. But please don't hesitate to reach out, especially if you're feeling lost or confused, or actually even more so if you're feeling frustrated. This is a learning experience for all of us, so we'll just get through it together. So please check out the homework. It is due tomorrow. It's not very long. And tomorrow I will be posting another video, probably not in the morning. I'll give you a little bit more time. But probably tomorrow evening or something, I'll post a second video updating, doing more like mathematical problem solving with these ideas. All right. Thank you all, and I'll see you later. But first, check this out.